Welcome everyone to the third installment of the Embedded Intelligence lecture series. My name is Evan Greenberg. I'm joined here with Gil Akos of ModeLab and Skylar Tibbits of the MIT Self-Assembly Lab. Skylar will be giving a presentation on material intelligence as the third part of our series. I'll just give a very quick presentation on what the Embedded Intelligence lecture series is about and introduce Skylar Tibbits. Okay. So as you are listening to Skylar, if you have any questions, please send it to our Twitter account at @embeddedintel_ or use the hashtag embeddedintelligence. Embedded intelligence is a design model whereby exploring the intrinsic properties of material, biological, and machinic systems produce novel strategies for design. All materials are embedded with implicit capabilities. By manipulating these materials through simple actions, we can begin to develop an understanding of their inherent properties and explore ways to exploit these in the design of material systems. Material systems can be further developed by exploring the many ways in which natural systems use similar strategies to sustain effective performance. Design can be enhanced by exploring the inherent capabilities embedded within fabrication systems and how these can inform design strategies in order to produce novel material effects. The Embedded Intelligence lecture series aims to interrogate these three main lines of inquiry: material systems, natural systems, and machinic systems, which comprise the notion of embedded intelligence in architecture and design. Each presenter will deliver a lecture built around a series of curated questions pertaining to the subject matter, streamed live on Google Hangouts. The series ends in a roundtable discussion with the curators in person at the AA and on air around the world, investigating a series of prototypical case studies designed through the model of embedded intelligence. So today we have Skylar Tibbits talking about material intelligence. Skylar Tibbits is currently a research scientist in MIT's Department of Architecture, teaching graduate and undergraduate design studios and co-teaching How to Make Almost Anything, a seminar at MIT's Media Lab. Skylar was recently awarded a 2013 Architectural League Prize, the Next Idea Award at Ars Electronica 2013, the Visionary Innovation Award at the Manufacturing Leadership Summit, the 2012 TED Senior Fellowship, and was named a revolutionary mind in Seed Magazine's 2008 design issue. He has worked at design offices including Zaha Hadid Architects, Asymptote Architecture, and Point B Design. He has designed and built large-scale installations at galleries around the world, has been published extensively in outlets such as the New York Times, Wired, Nature, Fast Company, various peer-reviewed journals, and books. MIT's Self-Assembly Lab, directed by Skylar Tibbits, focuses on self-assembly and programmable material technologies for novel manufacturing, products, and construction processes. So once again, if you have any questions live as you're watching, please send them via Twitter at @embeddedintel_. And I'd like now to introduce Skylar Tibbits.
Yeah, thanks so much, Evan. Thanks, Gil, also for the invitation. So what I'm going to do is present some of the work from the lab, and then I guess we'll hand it over and we'll have some Q&A and discussion, etc. So I'll share my screen. So Evan, let me know if anything's going wrong. I can stop as well. So as you heard, I run the Self-Assembly Lab at MIT. We're within the Department of Architecture, which is for some people quite unusual, but for us, I came from the Department of Architecture. I came from that background. I then came to MIT to study design computation and computer science. And for many of us, software and computing is part of everyday life, and it's radically changed the way we design. For myself, this is quite an inspiration. This is 1963, Sutherland's first CAD tool that came out of MIT. So there's a long legacy of how computing can change the way we design and change what we design. But to more traditional and contemporary techniques today, there's lots and lots of work going on in algorithmic processes and new generative scenarios that produce complex geometries, massive iterations, evolutionary solvers, simulation tools, etc. So it's without question that software has radically changed the way we design. And so I think about that as code as a new language for design. This is 1952, the first CNC machine at MIT, again with contemporary counterparts like multi-material printing, CNC machines, laser cutters, water jets, you name it. So also without question today that there's been a hardware revolution, and computers linked up with machines have radically changed the way we produce things. So we think about that as code for design and now code for machines. The research lab really focuses on the next step of that, which is code for materials. How we can embed different capabilities that we've become used to in the digital world, like reconfiguration, logic, sensing, actuation, error correction, all of those sorts of properties we want to embed directly in the materials themselves. So we think of that code for materials, and where we're going is code for construction. How we can rethink the large-scale industrial processes of the human-scale world. So you can think about construction, manufacturing, product assembly, distribution. All of these processes are fundamentally different than the way materials and structures are assembled at other scales. You can go all the way down to the smallest of scales, atomic resolution or nanoscales. In fields like biology, chemistry, material science, there is no top-down assembly. There is no humans slaving away, whacking at things, forcing materials coming together, machines that manipulate things, that build, precise things from top-down instructions. If you go all the way up to the other scale, like astrophysics, for example, there's also no top-down assembly. And so it's a curious question for us and leads to exciting opportunities, and we're proposing that there's new possibilities for each one of these sectors that could potentially radically transform the amount of energy, the efficiency with which we build, what is possible to build, how we collaborate with humans and machines, etc. So we focus on a phenomenon that's obviously in the name of the lab, the self-assembly, which is a process by which disordered parts build an ordered structure through only local interaction. So that means you have a bunch of parts, you subject them to energy, they should be able to come together on their own without human or machine input. This is a phenomenon that transcends every scale, every discipline and domain, etc. But it's something that we don't use and is not an intuitive process at the human scale. And so, we've worked on a lot of different projects that try to demonstrate this at many scales with many materials, different environments, etc. Probably the most obvious or straightforward implementation that we did was a project in 2012 with molecular biologist Arthur Olson and Autodesk. And we built 500 of these glass flasks. So you shake it hard, as you saw there, and it breaks. You shake it a little bit softer, yet randomly, and it comes back together. So we're interested in a number of properties here. You can build non-random things from random energy. So you use non-guided, non-instructed processes, and you can produce very precise things. You can have noisy, messy, error-prone materials and build structures that are more accurate than the parts themselves. Children are just as good, if not better, than adults. There is no skilled labor. There are no instructions. You don't have to know anything about the thing you're making to be an expert, quote unquote. So this radically changes the way we look at construction. It goes against every process that we know in terms of having skilled labor, trying to make more and more precise machines, guided instructions and energy, etc. So it's kind of the fundamentals that we study. We then went a step further, which showed chirality, so right-handedness and left-handedness, again with Art Olson. This is showing a biological principle that allows you to have the exact same parts encode different assembly instructions and therefore always ensure that you have fully black and fully yellow. You'll never have half and half, and that's fundamentally based on error correction. So if two parts connect in the wrong way, they'll be weak and they'll break off. And no third part will be able to bridge those two. So what we do is when two parts are accurate, they start to grow. And they start to assemble stronger and stronger structures, which weeds out weaker error-prone structures. So therefore, you can guarantee you get the two structures. And both of those projects are focused on manufacturing, in a sense, because they have a number of components. They come together on their own to build the same product over and over and over again. So you can look at that as a challenge to traditional manufacturing. But as a designer, we're interested in something called polymorphism, where you have physical building blocks that can be assembled in many different ways to make many different things. So you can think about carbon that forms itself into graphite or diamond, the same exact fundamental components that come together to produce drastically different materials based on their environment, based on their interaction with one another, etc. So we're interested in that. How do we find the fundamental building block that can come together in different ways and produce both local patterns and global patterns? Locally, we're interested in single chains, hexagons, pentagons, polyhedra. You can see here a snapshot from some of that work. On the right, you can see a hexagon, or no, sorry, pentagon, five-sided object there, and there's other local patterns that emerge. This is the first time we also went into fluid environments. So we use neutrally buoyant particles that move around in a fluid tank, and we can control the energy in the system, we can control the patterns, etc. But the other pattern that we're interested in is the global pattern. So locally you have the local shapes. Globally, as we change the turbulence in the system, we're essentially controlling the temperature. So we're controlling the environment. If you blast it, you bring the temperature up, which essentially turns it into a gas. So all the particles break. If you lower the temperature, it then forces the particles to clump into more crystalline structure like a solid. You can move the location of the pumps, you can change them and study all of these parameters. But we had a few main critiques of this. One of the critiques is the monkey and the typewriter scenario. How long would it take for diamond to show up? And if diamond showed up, would we even notice it, or would we be able to use it? And the answer to all of those was probably no. That it would first of all potentially take too long, and second of all, we wouldn't recognize it and we wouldn't be able to take it out of the tank, because when we took the objects out, they all break apart. So we then started to look at lattices. Lattice structures could both be visually recognizable and they could be structurally stable, so we could take them out, test them, throw them back in. This was a collaboration with Neil Gershenfeld's lab, who recently showed a paper that demonstrates the world's lightest, strongest materials macro-scale composite lattices. But it's a challenge because it's difficult to assemble these lattices because they're made out of many components. So we were trying to study how lattices could be built in large tanks. So this is a bigger tank of water, 500 gallons. We have a number of pumps at the bottom. Right now what you're seeing is just a very constant, low speed pump. So the energy in the system is very low. And over the course of one night, so we filmed this overnight, it accumulates into a single crystal. On the left-hand side, you're seeing the video. On the right-hand side, you're seeing some early tests that we were doing on tracking. So we're trying to characterize the structures and at least location and density, because visually you can't tell from one moment to the next what's happening. Is it converging? Is it diverging? What's the entropy in the system? What's the global pattern of movement, etc. We've now been able to get it to roughly an hour. So what we do is we blast energy in the tank, we can break all the particles up, and then we quench it. And this is a principle that happens a lot in crystal research, where they quench it, and then all the particles can accumulate in the center. But what we're interested in here as well is how the global patterns can emerge. So locally, we can guarantee that it'll be a cubic lattice. So all the particles will come together in a cubic formation because of the shape, but we can't necessarily globally guarantee the boundary condition. So we're interested in looking at the different patterns of energy, like vortex might create a tower, or linear lift might create sheets, for example. But all of that research was showing same components coming together to produce different things, either a repetitive structure or a crystalline structure, more of an aggregation, but they were all the same. In this project, all of the components are unique. So all of the components are different, nothing is the same, they come together in different ways. So every part has to find exactly the right place in the global structure. It only has one location that it can fit. Everything else is not correct. So all the components come together and make this chair, which shows that you can make differentiated yet potentially hierarchical structures that don't cross-link, that find the right location, etc. So right now we're working on a few versions of this where you can make other structures, you can have larger numbers of unique components, you can make scaled up. And when I say scaled up, I think about two ways. One way is that you scale the thing up literally, so you make larger pieces. The other way is that you make many, many. So you take advantage of the massively parallel process. So you can make many, many, many chairs at the same time. But the other version of that is scaling up literally, so larger components. In this case, we did a project with 36-inch diameter weather balloons. So those weather balloons are neutrally buoyant, just like you saw in the tank. And one of the main implementations here was that we were able to use Velcro. And in many of the previous projects, we used magnets. And that sounds like not very novel that we were able to do that. But for us, it's a big step because it shows that the pulling force has nothing to do with it, that it's not about the attraction of any of these particles, it's actually just about stickiness and encoding the correct stickiness. So basically, particles move around, they bump into one another, and all you have to do is get them to stick when they're in the right location. They should break off if they're not in the right location. And so we encode some of that potential quote-unquote intelligence in the way that we have these nodes. So every node can connect to every other node. If it's not accurately linked up, so meaning if it's not on the axes, then it should be weak and it'll break. If it is, it'll be strong, but it can freely rotate. And that single degree of flexibility or single degree of freedom, that rotation allows for error correction. So here you'll see a large example of that. We did 36 of these weather balloons in the courtyard at our lab. So they float around. They're more or less neutrally buoyant. They're a little bit heavy so that they wouldn't float away. And then we threw a party. So people come and they throw the balloons up in the air. We had fans at the bottom, and those fans allow us to control the turbulence. You can see some of the single connections here. So balloon to balloon on the Velcro. And then you can see here some of the patterns that emerge. So you see a cubic structure emerging here, and there's two cubes here. There's more of a elongated, like beam structure. So it makes this cubic lattice like you saw in the previous one. And where we were going with this is that you could potentially use the airspace above the ground to build very large, lightweight structures. So here you see one of the researchers, Carrie, who can lift 10 by 10 by 10 or just over 3 meter cubed volume. So essentially a large space frame structure that you can lift in your fingertips, and then when the helium dies out from the weather balloons, you're left with this large lattice or space frame that would be much heavier, maybe impossible to lift. So we're thinking about all different environments, different scales, different connections and energy, different control of turbulence, and looking how these processes are possible at human scales. But I would still argue that all of this research is our fundamental or our basic research. So there's generally two categories of research. There's fundamental and basic research versus applied research. And this, we're still just trying to understand it. We're trying to see what are the natural ingredients, what is possible, how does it scale up, and then eventually transition into more applied research. The other side of our research at the lab is much more applied. And this is what we call programmable materials. So our programmable materials work is the idea that you want to program physical materials to change shape or property on demand. So you want these tunable functional characteristics, and you want them to be able to repeatably and precisely transform themselves. There's a few fundamental ingredients that we use when we do this. So the top left are the materials and geometry. These are like the properties. So we link the material properties with the source of energy. So in this case, wood, you might use moisture, or heat, you might use metal. Polymers can use all sorts of different energies. The properties also have different mechanical properties afterwards, but the amount of material and the shape of the materials dictate the performance. So if you put more material, it tends to be stronger and slower to transform. If you put less material, it tends to be faster and weaker. You can put different layers. You can design this macro scale composition to have different types of mechanical transformations. So you can get folding, curling, twisting, shrinking, expanding, etc. And we look at this research as macro scale material science, that we're not inventing fundamentally new materials, but rather we're combining existing materials in new ways to get radical new properties. And that's kind of how we approach the vision of programmable materials. One of our first implementations of this, and maybe the most notable work that came out of the lab so far, is what we call 4D printing. And this research was a collaboration with Autodesk and Stratasys. We called it 4D printing because we wanted to add the element of time to printing. We didn't want to print things that were done and that would just sit on a shelf or be static, but rather were highly active, that they would transform, change shape, reconfigure over time. So it's much like the field of smart materials, but rather because we're printing it, we can fully customize those materials. We can control their properties, we can control their structure, how they transform, what energies they're activated by. So you have full customization with smart materials. And it's also a lot like printing robotics, but we're eliminating all of the wires and motors that make robotics expensive, failure-prone, and difficult to assemble into products, for example. So we've now done lots and lots of different configurations. And the way that we do this is using multi-material printers. So you can print with many different materials at the same time. In this video, you're seeing two different materials. One of them is just a rigid black polymer, which I think of as the braille. It's the geometric or mechanical information. So it encodes all of the angles, the joints, the precision, the structure, the backbones. It is the information or the code. And the other material is an expanding polymer. It expands roughly 150% when it meets moisture. So that gives you the activation energy to transform from one shape to another shape. And we've shown precision over transformations in all different types of mechanical transformation, like folding, curling, stretching, twisting, etc. We can go from any one shape to another. With Autodesk, we've tried to design a lot of capabilities in how we simulate that, and that's become a long-term project, but also more of a conceptual one, in the sense that we've taken the strategy where if you really want to simulate lots of different transformational materials, there's lots of researchers working on this. You don't want to have to go all the way down to the minute details of that material. So rather what you want to do is a geometric transformation that uses extracted data from physical models, so you can simulate many, many materials, and it's easy to plug and play between those. And you'll see some other examples later on that. The first demonstration that we showed was a single strand that has both of those materials embedded in it, and it transforms into the letters MIT when it's dipped in water. So we showed a single strand that goes to a precise two-dimensional shape. We showed two-dimensional to other two-dimensional, like other text and complex shapes. In this case, we went from 2 dimensions to 3 dimensions, and I think it points out a few fundamental capabilities. One is that you can minimize printing time. Printing is very slow still today. There's lots of research going into that, but if we can print flat materials or minimize the amount of material we're printing, you can then have it transform into much larger, more complex things that would take longer to print. But you can also minimize the support material. If you compare the flat sheet versus the three-dimensional structure, we have a lot less material printed in the flat sheet, obviously. But then it also points to the shipping and distribution opportunities where you can flat pack things that then transform themselves on the other side. One of my favorite examples is this, where we showed flat sheets that transform into positive and negative double curvature. And this actually comes from my undergrad thesis, which was about describing doubly curved surfaces from flat sheet material using planar quad tessellations. But now it goes into flat sheets that can autonomously form those doubly curved surfaces. And by controlling the local expansion and contraction, you can then precisely dictate how it transforms into positive and negative. Maybe one last example from the 4D printing work is this prototype that we developed, which goes in a different direction. Again, back to the design side, all of the examples you've seen on our 4D printing work show a single material that transforms into predetermined shapes. In this case, we're trying to say maybe the design solution is open, and it actually depends on how the material responds to the environment, the amount of energy of activation, the time that it's in its environment, and that solution can emerge. So we print a gradient distribution of two different materials, and depending on the amount of time in the environment, the middle 15 minutes or the right at roughly an hour, you get drastically different shapes. And so we're interested in that as a potential solution for different domains where maybe the final output could find itself, so that the material could optimize for aerodynamics or for some performance criteria, and you don't necessarily need to predetermine that. But one of the fundamental questions that came up after we did that work from many of our collaborators, ourselves, and many different companies that approached us is, how do we do this with real-world materials? There's some nice things about printing, but there's also lots of constraints in terms of the material properties in the process. So is there a way to program every material, to program with other industrial processes and other fundamental materials so that it can be more near-term and have many more applications? So we started to build a huge team of collaborators around this field of programmable materials. And I actually categorize programmable materials as much broader than 4D printing. The 4D printing would be one subset. It's one way to program materials to transform using multi-material printing. But there's many others. There's many other industrial processes like bonding, weaving, spraying, laminating, many other different ways to activate materials or produce materials that can be activated. And the team is made up of product designers like Christoph Guberin, who showed a project where it's self-folding paper. You print on paper and then it folds itself on the other side. To Eric Demain, mathematician and computer science, algorithms for folding, materials developers like Carbitex and carbon fiber, software developers like Autodesk, for example. So we've shown three fundamental materials that we believe are highly programmable and transformable. One is carbon fiber, the second is textiles, and the third is wood. So in the wood example, there's a long lineage, especially in the architecture world, of using wood as a transformational material. So you can look at Japanese joinery using moisture to make more precise and stronger joints. You can look at Eames furniture using moisture to then produce shapes that wood was previously not capable of. And you can look at Achim Menges in University of Stuttgart using wood veneer to curl, and there's a long lineage of that at the AA and MTech. But there's two main challenges that I see. One of them is on the Eames example. There's lots and lots of energy, human labor to force these sheets into place. So you have to build molds, you have to have huge steam chambers, you have to force the wood into shape. So it doesn't do it by itself. The second constraint with the veneer is that you're limited by the grain direction. So I always think about it as this conundrum where if I want to produce a piece of wood that transforms into the letters MIT, I don't want to have to go to the forest to find a tree that has MIT inside of it. I want to be able to produce a grain pattern that can do anything that I want. So what we do is we actually print wood. So we print wood so that we can control the grain, we can control the curvature, the density, the two-dimensional and three-dimensional property of it. So here you see two examples that have different grain patterns, both that were subject to moisture that can transform in drastically different ways, showing positive and negative curvature. You can do precise folding to any arbitrary angle. You can do here a sine wave or positive and negative curvature again. So you can produce these material substrates that have any curvature or any grain direction that you want, much like the 4D printing, but you're using the properties of wood. And then we had a kind of cheeky nod to the Eames showing this self-folding elephant. So you can produce custom flat sheets, arbitrary structures that then transform into precise things. The second material is our textiles, and there's two ways to do it. One way is a more passive way. There's a pre-stretching and a jumping. In this case, you're seeing an active transformation. So it's heat-activated textiles that open and close for breathability comfort or weather or environment mediation, for example. We recently did a project in Milan. This was with a company called Woodskin that takes that a step further. So this is a textile and wood composite structure that jumps into place. So the vision here was that you would produce this thing flat, ship this thing flat. It has the potential energy embedded inside of it, and you just bump it or pull it up slightly, and then it jumps into place. So you don't have to assemble it. You don't have to put all these different materials and connectors together and kind of sculpt the piece that you want, but rather you just kind of nudge it and it jumps into shape. We've done lots of different work on connector details and the combination of woods and polymers and textiles that can self-fold themselves. Christoph's working on shoes, and we're working with different apparel companies and sportswear companies. The last material in the programmable material side is the carbon fiber. So we've worked with a company called Carbitex. Carbitex produces the world's only flexible carbon fiber. So it's fully cured and designed to be flexible, and they can spot it so it has different degrees of flexibility in different areas. And what we do is we print active materials on and within it. That allows it to then fold, transform, curl, stretch, etc. In this case, it's based on heat, but we also can do it based on moisture or light, potentially other activation energies. So here you're seeing real-time, super fast, repeatable carbon fiber that can transform itself. On the left, you see a simulation here, and on the right, you see the physical prototype. So we can use the exact same simulation tool with our 4D printing work as we can with our carbon fiber, as we can with our wood, as we can with our textiles. And that's because we can produce these prototypes, extract just simple fundamental data that says if I print this much material in this configuration, what shape will it transform into? You can input that into your model, and you have a quick, easy representation of the geometric transformation that it will produce. So you can move forward with design fairly quickly. But there's lots and lots of work to be done on the simulation side as well. I'll show two quick industrial applications that we're working on. So one of those is with a company called BAC. They're out of the UK, and they make a street legal supercar, the Mono. And we worked on adaptive aerodynamic panels for this. So Autodesk did a bunch of simulations for this, looking at the CFD, or the fluid dynamics, aerodynamic simulation, where you can induce drag. So their whole concept was that this is a street legal car. So let's say it becomes a moisture-rich environment, or it's about to rain. We want the aerodynamic panels to morph in order to induce drag on the rear tires. So we want to actually make the aerodynamics worse, which puts a downward force and increases traction when it's wet. And then as it dries out, it can curl back down to become faster. So you can control, or you can tune the aerodynamics. And this has been done for a long time in Formula One, or you can look at a Porsche, and the rear wing is morphing. But all of that is done with electromechanical actuation, or nitinol, or other types of both energy-intensive and weight-intensive actuators. And so this was demonstrating that we can do it with a single material sheet that is just responding to its external environment. So it's super light, it can be fast, and potentially just as responsive. The other application is we're working with Airbus on an air inlet for the top of their engine. So at the top of the engine, there's this hole, and it cools the engine as it flies, but it causes a lot of drag. And so in the exact same challenge, they could have traditionally applied electromechanical flaps like they have on the wings, but it would add weight, it would potentially fail, and then you'd need a control system back to the cockpit. So they came to us with a challenge: could we produce a self-morphing valve, essentially? So it's a single sheet of carbon fiber, super lightweight, it's completely autonomous, and it opens and closes in this first prototype based on temperature. So as the plane takes off and then arrives at 30,000 feet, there's a drastic temperature difference. And so we can take advantage of that to transform the air inlet. That sounded like a good idea until you think about landing in Antarctica versus Arizona. There's obviously a different temperature delta there. And so what we started to move to was pressure differential. So we're now looking at pressure differential as an activation energy. Here you're seeing the prototype in the wind tunnel in Toulouse. And as the wind speed increases, the flap jumps, and then as the wind speed decreases, it goes down. So we can control where the flap is in the open or closed state simply based on the wind speed of the plane. And so the way that we do that is we produce bistable or potentially or even more these stable structures based on the heat-activated transformation or other forms of transformation. You could use light, for example. And that produces a mechanical bistability, which then jumps into place when the differential pressure changes. So you can think about this like when you're driving down the highway and you open your window, the prototype or something else that you have in the car might fly out the window because of this pressure differential. So what we're trying to do is make it so that when that happens, it jumps into a very specific predetermined shape, which controls the airflow. So all of this work, both the self-assembly work and the programmable materials work, I think is really addressing this main challenge. This image to me is the antithesis of our work and is actually where we were enslaved in projects, and many of our students are enslaved and many of our colleagues, and I'm sure at the AA there's lots of people enslaved in their own projects, which means that you've designed these massive things that we're going to build, and they're made out of thousands and thousands of components that need to come together in super complex ways that take lots of friends and cheap labor and lots of students not getting paid enough, and or lots of expensive contractors to build these things. And they come together in complex ways. They take lots of energy, they take lots of time, they're super failure prone, they have lots of complex instructions. And this is the antithesis of what we want to do, that we're proposing that there's new possibilities where materials can help you build better structures. Materials can potentially assemble themselves or guide you in assembly. They can give you information as you're assembling it. They can respond to their environment to design new shapes or new potential outputs that are far better than what you could have predetermined. So we're interested in a new model of that. And I think there's two major trends emerging. One of those trends is a shift between robotics to materials. You can see this across every research domain. You can see this industrially as well. That the previous mindset was we would spend lots and lots of money, throw lots of motors and mechanisms, and we would brute force our way through the problem. But as I mentioned previously, there's a lot of challenges in that. It's expensive, it's heavy, it's failure prone, it's hard to control, etc. And many of the researchers in this space are now moving to far more agile robots, soft robots, jammable materials, pneumatic structures, smart materials, or 4D printing or programmable materials, for example. And we're proposing that these materials can have logic, sensing, and actuation directly in the material themselves, that there is no need for external control in that sense. But we're being a bit utopian in the sense that we're not proposing materials can do everything that robotics can do. One good example is communication. Global communication away from your neighbor is quite challenging in materials. So we think about it as a relationship between materials, humans, and machines. That machines are really good at repeatability, precision, they don't get tired, etc. Humans are really good at creativity, abstract thinking, etc. And materials are good at physics. Materials understand the physical world. Materials can transform, they can respond, they can sense things that we can't sense, and they can be highly active. And so therefore we want all of these things to collaborate and to inform one another to potentially design better things. And the second is a bit more far out, a bit more utopian, and this is something that we call evolutionary fabrication. So I think about it as a critique to today's printing world. That if you think about 3D printers today, you send a file to the printer, and that printer gives you back something that's worse than you send it. It'll never give you back something that's better. So in the best case scenario, it would give you something that's just about good, and you won't even notice it, so it looks like it's exactly the file you sent. But realistically, if you went small enough scales, it's much worse than what you sent. It'll never say, you know, your design could be a little bit better if you changed this. Or what if you went this direction? Maybe we could produce something that would perform better. So what we're proposing is that we could use materials and the fabrication process itself as the design process. so that you'd have materials that are assembling, reconfiguring, transforming themselves, etc. And at the same time, we're tracking that and we're computing possible scenarios. We're weeding out potential wrong dead ends or wrong directions, and we're guiding. We're updating the energy in the system, we're changing buoyancy or changing material properties on the fly. And that allows us to potentially arrive at solutions that are better than potential predetermined solutions, but also can be reconfigurable. So I think about this as looking at some of the simulation that's going on today, where you take a block of material, a digital block, and you subject it to forces like topology optimization, and you arrive at some solution, and then you produce it. If you change any one of those forces, your structure is extremely weak. So what we want to do is have materials that can adapt on the fly and potentially arrive at new solutions that we couldn't have preconceived. So I'll leave it here with a quote that I think sums up the vision and where we are now, where we're going. We believe it's now possible to program nearly every material to assemble itself and transform in radical ways. And this is our lab at MIT. As you can see, we have big tanks of water and tumblers and fans and lots of crazy, weird environments and energies to activate materials. And I welcome you guys to come visit us if you're ever in the lovely city of Boston. But maybe I'll turn it over to you, Evan, and we can go to questions.
Great, thanks. Thank you so much, Skylar. It was a fantastic talk. We have a live audience here. Maybe we can thank him by giving him a round of applause. So we're going to start Q&A now. Remember, anyone live here at the AA or watching online, if you have any questions for Skylar, please send them to @embeddedintel_ on Twitter. And now we'll pass it over to Gil Akos to start off the Q&A.
So echoing the same sentiments, really great talk. Even though I've seen it a couple different times, it's always new and different. So that was really exciting. Thanks for sharing all of the work and especially the new work. I'd like to start by kind of circling back to the origins of your presentation, and we were looking at some of the kind of early CAD applications way back when. And you were talking about how code is a kind of new, or we could say maybe a newish language for design. So that's something that now has a heritage of, let's say, 50 years or so. And we know that material is a language for design as well, and that heritage goes back centuries, if not farther. Is programmable matter a new language? Or can you speak a little bit more to how you might see that as falling within that conceptual model of it being a language? Or is it maybe a hybrid of things that have come before?
Yeah, I think it's a convergence of a lot of technologies and developments. I actually got started on this when I came to MIT. I was on a programmable matter grant from DARPA under Neil Gershenfeld at Center for Bits and Atoms. And there's lots of different people on that grant. And if you look at every one of them today, they've transitioned from the notion at the time, which is nearly 10 years ago now, that robots were programmable matter. That if we just got robots to be autonomous, modular, small enough, all of these modular robotic things that are from this big to huge, that was programmable matter. And almost every single one of those researchers, we just had a summit here at MIT called Active Matter Summit. A lot of those people were there. It almost became a joke that it's like the DARPA summit because all of these people reunion. But every one of them transitioned away from that and is doing active, soft, highly agile, flexible, reconfigurable things, which brings me back to this idea of materials, because I think that you can look at the software revolution in any space, but in the design space specifically, which led to many, many, many of us thinking, okay, after I produce this crazy thing in Maya or Rhino or Grasshopper or whatever it is, what do I do with it? So that led to this whole boom of digital fabrication. Every school had CNC routers, laser cutters. More recently, there's an arms race with robot arms, for example. And that led to more people focused on materials, because it's like, okay, I have all these crazy machines. Well, now what do I do? And I want to actually investigate the materials that we build with. How can I make better materials? How can I print with new materials? How can I make hybrids, etc.? MTech has been doing that for a long time, and many of us have been investigating in that. But as you said, there's like a lineage, centuries looking at materials. In some ways, I think we lost it. We lost that ability, maybe because of the Industrial Revolution, that we just thought like we can whack away at materials and they're our slaves. Like we just standardize stuff. So we look at 2x4 construction with wood as a standard industrially produced material instead of looking at the anisotropic properties of it, for example. But now there's this resurgence, both because we have computing possibilities, we have machine possibilities to fabricate things. We're now interested in the properties of the materials, as well as the revolutions happening in synthetic biology and material science right now. They're like booming, those two fields. So there's this huge technological development happening in materials, which fundamentally allow us to program them like we did computing and machines before.
I think that's a really interesting way to kind of segue into my question. I think you talk about the the arms race with robotic arms and all of the different kind of fabrication tools that we have and the techniques that we're using now. But how do you kind of see the future of materials? Is it about innovating around the materials themselves or the processes that we design to act upon them?
I think all of it, right? There's material scientists that are making amazing developments and fundamental new materials. In the EU, I think there's a Center for Directed Self-Assembly, which is just looking at how you arrange particles to create new formations, like graphene, for example, how you invent new materials just by rearranging the fundamental components. You could go to synthetic biology and you can look at programming bacteria as another world and the whole iGEM competitions and stuff. So people are looking at materials on like every single length scale, every single domain, up to the macro scale perspective, which we take. It's about more how do you combine those to get new properties. We don't necessarily invent fundamental new materials, but rather we try to combine in new ways. And so then the question becomes like, what do you want the material to do? What is the application you're going for? What kind of radical properties can you get? And also, how do you design around it? And so then that comes back to the tools. Like, what kind of design tools, machine tools, hardware tools do we need in order to program these materials? So I think it's happening because of the convergence, but then they're all feeding back to one another, just like the hardware boom is feeding back to software. It wouldn't have happened without software. It led to new software developments, etc. They're all kind of intertwined.
So if there's, let's call it a new approach to materiality that's enabled by other trends that are happening, both digital, physical, robotic, etc. Taking it back to kind of process and approach, are there key things that the creative professional today that wants to explore this approach to materials needs to keep in mind in order to be successful?
That's a good question. I don't know that I have a direct answer for it, other than a lot of times it feels like we're in the early days of chemistry, or we're in the early days of cooking, for example, or the culinary arts, or early days of any of these art forms, or gardening, or whatever. And I look at these domains because, let's say gardening or cooking, you have no control over the local interactions. The only thing you have control over is the ingredients and the energy. And by understanding the ingredients and the interaction with their environment, you can produce things that you couldn't have produced otherwise. So you can't sculpt a flower. It just won't work. There's no possible way to do that. The only way you can do is let it grow by giving it the right environment and kind of dancing with it. So you're really collaborating with the materials and the energy. And so I look at those domains, but think about the early days. Like, we're just screwing around. We're just trying to figure it out. We're throwing shit together and seeing what happens, and like trying to build up a language, trying to build up the tools. We don't even have like the microwave. We don't even have the the fundamental tools, or the oven, or whatever it is. So everyone is kind of out in different domains, working on different scales and different applications. There's no fundamental like ingredients cookbook that like we all share, and there's not even software tools that go between our lab and like a biologist lab or a material science lab. So, we're trying to build all that stuff up, but it's going to take a while. And I think on the actual materials transformation side, we're a lot further along. On the assembly side, it's like way early days. So I don't think I have fundamental principles, but
what about lessons? What's like one or two lessons that someone who's newly approaching materials in this way might be able to kind of get started?
yeah, one of them I think relates to like issues of entropy and talking about force versus like forcing something versus like dancing with something. And we always go back to that. Like the more we try to force something to happen, the worse it gets. So maybe two quick examples, like if you look at the flasks that you shake and they assemble, like if you try to make it assemble, you're super bad. It's like the worst you can do. If you close your eyes, you're actually really good. So you have to find a way to like let go, like release control, and good things can happen, and be open to surprises. Like let it move, take an opportunity when you see a surprise, and then kind of dance with it, both as a design thing as well as an assembly thing. Another example is I look back at like precision or tolerance control. If you want to build a structure, the more you try to force accuracy in every single component, the worse you're going to be. So what you really need to do is find a way for redundancy to creep in, for error correction to creep in, and like use your degrees of freedom in the right way. There's lots of principles in mechanical engineering about that. I think about it as a simple example. If you want to build a circle out of discrete elements, you probably shouldn't try to precisely control that angle at every single step, because by the time you get around, you're going to be way off, because there's tolerance in every one. But if you let a little bit of freedom, as it comes back, it's going to then close itself and it error corrects as a whole. And that's kind of a principle that we try to achieve, is like not forcing everything, letting go of control a little bit, and you can potentially achieve better results.
So in kind of discussing this, let's say even the issue of tolerance, I think that brings back the idea of scale, and how you deal with material at different scales. So I mean, you showed a series of projects that cross over, let's say, from the kind of handheld or desktop experiment to the much larger, the balloon experiment, and a lot of your references also maybe materially don't scale, but one question that I have is, does the logic that you work through, how do you scale through the logic, and what do you see as your limitations?
Yeah, so a core belief that I have, and I'm trying to instill in everyone in the lab, is that the principles scale. Nothing else scales. Like the materials don't scale, the forces don't scale, but the principles scale. So that means that at every time you switch scales, you need to change materials. You need to rethink force. Like we have gravity at human scales, nanoscale they don't have that. We don't have van der Waals forces, they do. You probably can't use the same material at the nanoscale that you can at the macro scale. But if you don't look at it as a negative thing, and you're not trying to literally translate everything, but you're trying to translate the principle. So self-assembly works at every possible scale, but you need to change things. And so you kind of need to work at the scale that you're given, and look at the right environments, the right forces, the right interactions in materials, and then it works. And so in that sense, logic and information are scale independent, and there's a lot of references there about looking at information as the thing that translates across all of it. How do you embed information into the construction process? How do those components know how to error correct, or know when they're the right one, or where's the blueprints in the parts so that adds up to the right thing? All of that scales. So the question is, how do you embed information in DNA, or how do you embed information at the cell level? How do you embed information at the organism level? How do you embed information at like a macro scale, synthetic material level? How do you embed it at a city level? How do you embed it at like an astrophysics level? Information scales fundamentally, so do the phenomena that we're working with, but you got to change all the other dynamics.
So my next question is maybe going up to about 10,000 feet or so, not at the conceptual level, but like organizationally. So you've got the self-assembly lab at MIT, which is its own organization that's in the midst of a lot of really interesting things going on, not only at Cambridge, but in the related fields that we talked about. You mentioned mechanical engineering. We're talking about biology and molecular sciences. As an organization, the self-assembly lab, one of the first things you said you did when you were looking to explore some of the applied experiments was to gather a set of collaborators. So my question is really, is the cross-disciplinary nature of the self-assembly lab something that's absolutely essential to the work you're doing? And if so, I'm kind of imagining it is, but if so, how does that mindset impact how you go about developing the experiments kind of in time?
Yeah, it's fundamental to it. We're in a center called the International Design Center at MIT, and it's quite unique because it's not related to any other department. So it isn't a department itself, and it's not related to any department. It's an independent center, and all the labs come there that are housed there, or there's other PIs, and we're all from different departments: mechanical engineering, biology, material science, architecture, etc. All of the students that come there are from every field, every department you can think of. In the lab, we have students from every domain, like computer science, architecture and design, material science, mechanical engineering, astrophysics, all different domains. And the undergrads at MIT are just super brilliant. They have just knowledge that is crazy and super inspiring. And they converge here, and we can teach them some things, and they can teach us a lot of things. And I think about it in the same way that when we collaborate, it's like trying to find a way to be comfortable in uncomfortable domains, or trying to use non-intuitive processes and find ways to make it intuitive. If you collaborate with molecular biologists or material scientists or physicists or whatever it is, you're going to be uncomfortable, they're going to be uncomfortable, and awesome things usually happen from that, and you learn a lot. You're not going to be an expert in those domains, but maybe you can make contributions collectively in both domains. So we don't try to, we try to be a bit humble when we're in other domains. We don't even really know what ours is. What field are we? We don't really know. But if you can collaborate with people, you can, achieve better things and then make contributions in many different areas. So, yeah, that's kind of how we approach it.
So we need to wrap up, but you say that you're not really sure where you sit in the in the world in a way. But I think one question that probably everybody wants to know is, so what's next? What's on the horizon for the self-assembly lab?
Yeah, we have lots of crazy projects going on. There's both industrially sponsored projects, so we have like very, very real world stuff, from apparel and sportswear to furniture stuff, some building materials and infrastructure work, orthodontics work and medical stuff. There's like super applied, and then there's super weird, wild, utopian, fundamental research, just trying to understand these things, scale it up, look at new properties, new environments, and all sorts of collaborations in between. There's some like larger, maybe proto-architectural work, and I don't know, all sorts of different things. So, we never really know where we're going, but it's like an endless search. We're always trying to find different opportunities and push the boundaries of different domains. Hopefully, never making incremental progress, but every step is like larger, radical progress.
Well, we're definitely excited to be able to see your next work published. We see the work of your lab out there every day, so we're really excited to see the next work that comes. So just want to thank. We're just about hitting time, so just wanted to thank you again, Skylar, for joining us and for giving a really fantastic talk, and for for wrapping up the lecture series in such a interesting and kind of exciting way. So thank you once again.
Sure, it was a pleasure.
And to everyone else who's watching, we thank you also for tuning in and for being a part. And just as all of the lecture series that we've kind of pulled together has been on the back of a design model that we've been thinking through that we tested last year in the visiting school, visiting school New York, embedded intelligence, which will be running again this summer. So we invite all of you who are interested to check it out at newyork.aaschool.ac.uk. We'll be running that visiting school from the 6th to the 17th of July in New York City. So we welcome you all to come discuss these ideas of material intelligence, biological intelligence, and machinic intelligence with us and kind of explore what those mean for architectural design. So thank you once again.